Oh, it's still really blurry. I wonder how you do it. I'm not going to fiddle. Anyway, so this is part D of the question that started with fish from component 3. And we've got a lovely scatter graph with a nice line of best fit that, you know, you're all desperate to do these lines of best fit. So, what's it showing us? The relationship between blood vessel lumen diameter and velocity of blood flow, and we can see really clearly that the wider the vessel, the higher the blood flow. State the type of correlation. So if it goes up and up, it is a positive correlation. That's a nice easy mark, isn't it? Use the graph to determine the gradient of the line of best fit. Jolly good. So for this a little activity, you'll need a ruler. Obviously the bigger the distance you can take it over, the better. So I'm going to take it over, that one seems to sort of have a nice little intercept on a line. I'm going to take it from 120. And remember, with a gradient you're looking for a change in one and a change in the other. And you're going to do the change in the y value against the change in the x. So coming down the graph, what have we got? Just take it over as big a distance as you can. So there's a lovely, is that a lovely intercept there? Lovely intercept there. There's an even better one at 60 actually. I'm going to take it, oh no, 60 is not good, that's halfway between. 80 is a bit close. 40, not overly convinced. 20, it doesn't really, I'll take it to 20. It's kind of right on the edge of the line there, isn't it? So let's go for it anyway. Oh, and that makes the numbers easier. I've then divided by 100 and that would be lovely. Love dividing by 100. Okay. So, for every 100 change here, so that's the one at the bottom. How much change have we got here? Right, let's look at the scale. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So that means each one square equals 2. So we've got 2, 4, 6, 8, 10, 12 at the bottom. And then we've got 60, 2, 4, 6, 8, 10, 12, 14, so that's 74. 74 minus 12 over 100 then. 74, and I know I should be able to do this in my head. 62 over 100, I can do that bit in my head, 6.2. Brilliant. Okay. If we'd taken it over too short a distance, I don't think we would have got as good a figure. We might have done. So we've got a 20 change there. That's sort of 58. It might have worked. I like to take it over a nice big distance. I just think it's easier. And I like dividing by 100. So, the equation for a straight line is y equals mx plus c, where m is the gradient. So that, what do we know about that? That's 6.2. Y is the velocity of the blood flow, x is the lumen diameter, and c is the y-intercept. We haven't really got one at the end. Looks like it'd be a minus number. Would you have a minus blood flow? Surely it just flows or stops. Anyway, on this graph, c equals 0. That must change gradient, perhaps. I don't know. Maybe it does. Anyway, that's 0. Calculate the velocity of blood flow. So what we're calculating, that's y. And we've been given a lumen diameter of 160 micrometers. So, we're calculating y, that's handy. Y equals m, 6.2, times x, which is 160, plus 0. Okay, 6.2 times 160. 992. That doesn't seem very sensible to me. 6.2 times by 100 is only 620. Six point two times oh, do you know what? I've divided by 10 instead of 100. So you see, checking calculations, so important. So 0.62, no, 0.62. That just didn't seem like a very sensible answer to me. That'd be like 900, would be like, but we're only taking it up to the next, yeah. So do you think, oh, is that answer sensible? Have I made a bit of an error here? So, right, y does not equal that, equals 0.62 times 160 plus 0. Right, now we're laughing. 0.62 times 160 equals, 99.2. That looks a lot better to me. 99.2. That makes more sense, doesn't it? That'll be like up here somewhere. Do not try and do these things. And it says do a calculation, do a calculation. Check it. I've just saved myself there a mark, which I would have otherwise lost, and probably another mark as well, which I otherwise would have lost. So 2 marks saved just by a simple check. God, I'm good. So, in the single circulatory system of a fish, oxygenated blood leaves the capillaries of the gill lamella, goes into systemic circulation, so that's around the body. Explain the importance of the relationship shown by the graph. So explain the importance of that positive correlation in the return of deoxygenated blood through the veins to the fish's heart. So, as I recall, single circulation goes like this. It goes ventricle, pushes it out, gills, goes into systemic, and then comes back into the atrium. So the point is that you're losing pressure there, yeah? And so that single circulation is slower and therefore less efficient. So first of all, I'm going to state the relationship, because I can't say how important it is unless I say what it is. See what I mean? So the wider the lumen of the vessel, the faster the flow. So remember what's depending on what. So this is our independent variable. The flow depends on how wide the vessel is, not the other way round. So blood, return of deoxygenated blood. So blood gets back to the heart faster. And why might that be? So without slowing down, because there is no contraction to generate pressure between gills and heart. That's the point, isn't it? It's lost its pressure in its gills, and then it's sort of going to sort of make its way back. So the wider the blood vessel, the better that will be. Okay. Whoa!